Have you ever just stopped, looked up at a massive skyscraper and thought, how is that thing still standing? Well, every single building, every bridge, every stadium you've ever set foot in relies on this kind of invisible engineering. It's like a digital battle that's fought and won against the forces of nature before a single piece of steel ever gets laid. Today, we're going to pull back that curtain on STAAD.Pro, one of the key pieces of software that, honestly, makes our modern world possible and keeps us safe.
So let's just start with that big, kind of crazy question. How does a massive tower of glass and steel take on the full raw power of a hurricane and just win? Or what about the violent shaking of an earthquake? You know, it's not magic, and it's for sure not guesswork.
The real answer? It all starts long before anyone breaks ground. It starts right on a computer, where engineers build a virtual twin of the building. And then they throw everything they can at it. We're talking digital winds, simulated earthquakes, the constant crushing weight of gravity, all to see if it will stand. This whole process is the world of virtual stress testing.
Okay, so let's dive right into this. At its core, every single structure we build is in this constant, silent fight. It's a battle against the relentless pull of gravity, sure, but also the push of the wind and even the weight of all of us and the stuff we put inside it.
And this is a field where the stakes are just incredibly high. This isn't some academic thought experiment. I mean, the entire field of civil engineering is really built on this one fundamental promise: keeping us safe and making sure things are stable.
So how do engineers get a building ready for this fight? Well, it all begins with building what you could call a digital twin, or a virtual skeleton. This is the very first step in the whole analysis, and believe me, it requires incredible precision.
Everything starts with something called nodes. Just think of these as the joints in that skeleton, the exact points in 3D space where all the important parts connect. Getting these right is absolutely crucial because they literally define the entire shape and geometry of the structure. Okay, so once you have your nodes, you connect them with beams. These are the horizontal pieces you see spanning across ceilings. Their main job is to carry weight, from the floor, from furniture, from people, and transfer that weight outwards to the columns, mostly by bending under the pressure. Right, so all that weight from the beams has to go somewhere. And that's where the columns come in. These are the big, vertical backbones of the structure. They take all the load that's been collected by the beams, and they channel it straight down, down towards the ground.
And finally, you've got the supports. This is how the digital model is actually anchored to the virtual ground. You have to tell the software, is this building fixed rigidly to a giant concrete foundation, or is it maybe pinned in a way that lets it rotate just a little? That connection is so important for getting a realistic simulation.
So, once that digital skeleton is all built and connected, it's time for the fun part. Now we get to apply the forces. We need to simulate every single kind of push and pull that the real building is going to feel over its entire lifetime.
Engineers start with two really basic categories: dead loads and live loads. Now, they might sound kind of similar, but the difference between them, it's one of the most important concepts in all of structural design.
The difference is actually pretty simple, but it's so critical. Dead loads are the constant, predictable ones. It's the building's own weight, the materials it's made from. It never really changes. Live loads, though, that's the unpredictable stuff. People walking around, desks being moved, snow piling up on the roof. The structure has to be designed for the absolute worst-case combination of all of these things happening at once.
And of course, it doesn't just stop there. For a skyscraper, you absolutely have to simulate wind load. The wind can exert this enormous dynamic pressure on the face of the building. And in a lot of places around the world, you have to account for seismic loads, those violent, unpredictable jolts from an earthquake.
All right, the model is built, the forces are all applied. Now comes the moment of truth. The engineer hits run, and the software performs that virtual stress test, calculating exactly how this digital structure is going to respond to everything we've thrown at it. So what is the software actually looking for? Well, it's calculating 4 key things. Bending moments tell you how much a beam wants to sag or bend. Shear forces measure the kind of stress that could literally cause a beam to split apart. Deflections, that's how much the structure physically moves or sways. And axial forces tell you how much a column is being squeezed or stretched. But here's the most important part. We're translating all that complex math into very simple, very high-stakes questions. Will it bend too far? Will it snap in two? Will it just buckle and collapse? The analysis gives us the hard data to answer those questions with real confidence.
You see, the analysis isn't the end of the story. Not at all. It's really the beginning of the design phase.
Now the engineer has to take all this data and use it to make the building not just strong, but smart.
And this is where the real power of the software shines. The analysis basically creates a heat map of stress across the entire structure. It shows engineers the exact beams or columns, the critical members that are taking the most punishment. That's how they know where they need to add more strength, maybe by using a thicker beam or a stronger material.
But here's the thing. You can't just make every single part of the building infinitely strong. That would be incredibly expensive and super wasteful. So the ultimate goal is optimization. It's this constant balancing act between safety, which is totally non-negotiable, and using materials efficiently, which impacts both the cost and the environment.
It is really important to remember, though, that a tool like STAAD.Pro is only as good as the engineer who's using it. A simple mistake, like assigning the wrong weight to a floor, or defining how the building meets the ground improperly, that can lead to a totally inaccurate analysis, and that's dangerous. This is where human expertise and just double-checking everything is absolutely vital.
So when you put it all together, STAAD.Pro and other programs like it, they act as this critical bridge. They connect the architect's beautiful vision on a blueprint to an actual engineering plan that guarantees that vision can be built to stand safely for decades and decades.
So the next time you walk into an office building or a stadium or even just drive across a bridge, take a second. Look at the beams and the columns around you. They're not just holding up a roof. They're the physical result of this incredibly complex digital battle that was fought and won, all to ensure your safety. What other invisible forces will you start to notice in the world around you?